Alright, so in this video we're going to talk about as to how we are going to work with TensorFlow. So the first thing that you need to do is you need to install TensorFlow, and you need to import TensorFlow. So you're going to do that by writing import TensorFlow as TF, and I have activated my Conda environment, which is Python 3.10, where I've installed my TensorFlow. To check if your TensorFlow is working or not, you can use the command of tf dot underscore underscore version underscore underscore, and you will see that indeed this is being detected. Now the next thing that we're going to do is, in this example, the first example, the hello example, we're going to be using the fmnest dataset, which is the fashion mnest dataset. So if you want to see what the fmnest dataset looks like, you can write keras fmnest, and then uh, let me write fashion mnest, and you'll see that we have 10 labels over here, starting from 0 as the t-shirt, 1 as the trousers, so on and so forth. And yes, if I show you the images, this is basically what it looks like over here. So you have different sorts of like clothes and wearable items in this in your fashion mnest dataset. So now what we're going to do is we are going to import this dataset. So for that we are going to be needing the keras library. So from TensorFlow we are going to import keras, and then from keras.utils we are going to import I think it's called image, yes, this thing, and load image. And also we are going to import another thing, which will be matplotlib.pyplot as plot, to show you guys as to how this dataset basically looks like. So the first thing is that we need to get our fashion mnest dataset. So for that we are going to write keras.datasets.fm fashion mnest, and we got our fmnest dataset stored over here. If I write this, you'll see that it is calling this dataset over here. Now we need to grab our images and our test images. So this will be train images comma train labels comma test images and my test labels from the fmnest.load data. So we have now loaded our data in our training images and also for our testing images as well. If you want to take a look at this images, what we can do is we can write plot.imshow, and since my type of training images is a num by nd array, then I can directly plot this over here. So let's take the first one, and the first image was a boot, and I can also say that print I can say train labels of this first image is 9. And what does 9 correspond to? So 9 is an ankle boot. Let's try something else. Let's take the first image and see what it says. It says that it is um, a t-shirt, I think. Yeah, t-shirt. Let me see if I can here grab. I'm not sure if this will work, but np.argmax. Yeah, I don't think so this will work, by the way. Whoops. Yeah, it won't work. So anyways, these are the labels, and this is how the image is showing up. Now the next thing that we're going to do is we are going to normalize the data. So as of yet, the images that we have for the fmnest dataset is for dimensions 28 by 28, and this is for some reason showing you the data with the colored map, but in reality the color is I think it's called gray. Yes. So in fact, your images are stored in black and white, they're not colored. So over here, what we're going to do is first of all normalize the data set, because uh, whenever you're doing computations in your machine learning projects, specifically for deep learning projects, you want to normalize the data. If you normalize it, the calculations becomes much more smaller, and it becomes faster for your gradient descent to work. So you're going to say that your train images will be train images divided by 255.0. So over here, the entire training images, so let's say the length of training images, there are 60,000 images in my train images, and all of them are being divided by 255.0 in this statement over here. And then similarly, you're going to do the same for over here as well. So let's call this test images divided by 255.0. So before before normalization, your train images 0 looks like these values, which is starting from 0 to about like 255 pixels. um, I believe yes. So 0 represents a dark pixel and 255 represents a white pixel. Now when we execute this statement over here, now if we rerun this, now you can see that every value has been squished down between 0 and 1. So that is the normalization step. The next part that we're going to do is we're going to create our model. So to create our model, let me go here and write from Keras. We are going to be importing um, layers, and over here we are going to say that our model is going to be Keras dot model, models, and then we're going to write sequential. So we'll be using the sequential AI API to create our model. And then the first thing that we want is going to be a layer of convolution 2D, and we're going to have 64 filter maps of 3 by 3, and we're going to keep our activation function as relu, and the input shape that we're going to give to this is going to be of 2828 by 1. All right. Okay, so we have an error over here. Maybe I think I've missed out the brackets. Yes, there we go. So let me add spacing so you can see where is which bracket being used. There you go. So how does a convolution 2D layer works? All of that part will be discussed in a different video where I'll be explaining you the theory behind it. But over here we're talking about as to how we can implement the theory that we've learned, and now we are implementing it in code. So for any reason, if you don't understand what these things are doing, you can always go to the TensorFlow documentation, and you can write keras.layers layers.conv2d. So over here, it can tell you that conv2d is basically used for convolution purposes. You have your filters, which was the first parameter that I gave. The size of the filter map was 3 by 3, and then all of the other information that you can see over here. You can also see some examples. This is not using the sequential API, um, and similarly over here as well. This is also the explaining um, the entire description as to how conv2d is working. Okay, so let me see if I can find sequential API for TensorFlow for you. Yes, there we go. So we have sequential, then we can define our layers, and the not in this way, but in terms of models. So keras dot models dot sequential. There we go, sequential model. So like this. So this is basically creating a normal neural network. Anyways, so let's go back, and we have defined our first convolution 2D layer. And whenever we write the first convolution 2D layer, it's always better to also apply a pooling layer as well. It's not always necessary, but it's always good practice to do it. So we are going to be applying max pooling of 2D, and we'll be applying 2 by 2. After this, we're going to create another layer of conv 2D, and over here we will be adding again 64 filter images with 3 by 3, and the activation will be relu. As you know, if we are going to add another max pooling layer, we do not need to specify any activation layer, because it acts as a hyperparameter, not a parameter. So your max pooling is not learning any parameters. And then at the end, what we're going to do is we're going to flatten this out, and then we are going to say layers dot dense 128. Set the activation to be, you can also use activation and write it as relu, or you can write it as this, which is tf.nn.relu. So you can use any sort of syntax that you like. I'm showing you as to how you can do it with both of them. And then we are going to add the last layer, which will be of 10 neurons, and the activation will be tf.nn.softmax. So why did we add 10 neurons at the very end? Well, the reason is because, let me get the model summary and then I'll explain to you as to what I did. So model.summary, we have this summary over here. Let's grab this and show this over here. So what we are doing is, one second, let me just quickly wear my glove. Okay, so the first thing is that we got an image we got an image of size 28 by 28, and there is only one channel because it is black and white. Okay, then we said, okay, we are going to apply the convolution layer with a filter map of 3 by 3, and there will be 64 of them. So when we apply 3 by 3, this will be 28 minus 3. The stride is 1, and there is no padding, so 28 minus 3 plus 1, there will be 26. Okay, so the resultant image that you're going to get is going to be 26 by 26, and since there were 64 channels of filter maps being used, therefore we will be getting 64 channels over here as well. And if you want to calculate as to how many parameters were trained over here, then that would be 3 by 3 by 64, and another one for a bias as well. So if my calculations are correct, this should be 3 times oops, 3 times 3 times 64. Whoops, wait, 3 times 3 times 64, 576. So 576 for this, and then 1 times 64 for the bias. So you're going to add 64 to here, so plus 64, and that will give you 640. So over here you can see that these were your training parameters, and this was the output shape that we got over here. Then what we're going to do is we're going to apply max pooling. So when we apply max pooling to this of 2 by 2 max pool, then it will divide this by 2 and the number amount of channels remains the same. So this will be about 13 by 13 by 64, as you can see over here, and so on and so forth. The entire convolution layer will work. Once we get to over here, we have an image of 3 by 3 with 64 filters, and then what we do is we flatten them out. So when we flatten them, 3 by 3 into 64, this is 576. So we get this as 576 neurons, and then we connect them with 128 128 neurons, like so, and then we connect them with the last layer, which is of 10 neurons. 10 neurons. Why 10 neurons? Because if you notice in the FNES, in the FMNES data set, so over here you have 10 classes. This is the reason as to why we added 10 neurons over here. And since this is a multi-classification problem, the the activation function that we are using at the very last layer is softmax. It's not written over here, but if we go to our code, we can see that it is indeed softmax. So we have created our model successfully, and now the next part is to define our hyperparameters for our training. So this will be done by writing model.compile, and over here the first thing we need to tell is our optimizer. So for people who don't know, whenever we're training a machine learning model, we are applying different like optimizers. We're trying to find the minimum function, we're trying to minimize the loss, and we can do that by using gradient descent. That is an optimizer or an optimization algorithm. So in our case, we will be using tf.optimizer Adam, and we'll be using our loss as a categorical cross entropy, but we'll be using sparse categorical cross entropy. Again, why are we using Adam? Why are we using sparse categorical cross entropy? All of this will be explained in the other videos. And we will set our metrics to be of accuracy. And we're going to compile this, and there's an error, which is there's nothing known as an optimizer. So I think so I need to let's see how to. I think I forgot the library which uses this. Okay, tf.pyros optimizers. Where is the example code? There is no example code. uh, hmm. It should work. I think I need to import optimizers. So from Keras import optimizers, and now if I run this, maybe I'm making some sort of spelling mistake. tf dot optimizers dot no no making some sort of mistake. Wait, hold on. Let me try to find the library for this. Uh, yes, wait, hold on. Let me try to find the library and I'll come back. Yes, so apparently it was optimizers. I just had to add an S. I don't know why when I was adding when I was writing optimizers, it was adding an underscore, so my IntelliSense was a bit bugged out. Anyway, so you have optimizers, and then you can train your model. So we will write model.fit, and then we want to train on our train images, our train labels, and then we're going to set our epochs to about 5, and we will train this, and we will see as to what accuracy are we getting over here. So till this is being executed, you will see that there are case scenarios where your model will overfit, which is that it will perform very good on the training images, but when you introduce your testing images, the accuracy is not so good. Um, if you want to also look at the performance at your validation data as well, then we can also include that. So let me do that as well. So um, let's see. Train, train images, train labels, and then let's set validation data to be test images and test labels. Hopefully this works. Not really. So this is not running. Oh, there's a comma over here. Yes. So anyways, I'll show you the validation in the next video. For now, let's see the performance on training labels. Um, but whenever the model is overtraining or it's becoming like, if your training becomes if your model becomes overfitting, which is that your accuracy becomes very very high, which is like about 0.99 on training or 1 on training, then that is a very clear sign of overfitting. So to reduce that, what we can do is we can write a callback. Okay, so we're going to write that right now. So we're going to create a class of my callback, and we're going to introduce tf.keras.callbacks.callback, and inside here we're going to say define on epoch end. We'll have a self, an epoch, a logs dictionary, and inside here we're going to say print, or before that, if logs.get accuracy, if that becomes greater than 0.9, then what I want you to do is I want you to print that with a new line that reached 90% accuracy, so we are canceling the training. And then after that we're going to write that self.model.stop training, stop training equals to true. And then we're going to create our object of callbacks by saying callbacks equals to my callback. Okay, so you can see that this is overfitting a little bit. If I would run this for more epochs, it would clearly overfit. So now we're going to add a callback to this, and we'll say callbacks equals to callbacks. So now we can see that on the first epoch, our accuracy is about 0.93. After this, the training will not resume because it has exceeded the 90% threshold. So let's just wait for this and see what happens. And as a result, you can see we have reached 90% of the accuracy, so we're canceling, and in fact we have cancelled. So this was the first very very light introduction for how you can create your own neural network and convolution neural networks on TensorFlow. In the next video, we'll be creating data pipelines to help us organize our data a little bit more. So let's do that very quickly. So we're going to call this cats versus dogs dot ipynb. So again, the first step for you to do is you need to import TensorFlow as TF, and then from Keras from TensorFlow you're going to import Keras. Let me see if my voice, yes, okay, my voice is being recorded. Um, then what we're going to do is we're again going to say that from keras.utils we're going to import image dataset from directory, and we're going to print our tf dot underscore version underscore underscore, and you will get your version over here. Now um, we basically have our cats and dogs dataset. I'll add a link down below in the video to for the link of this cats and dogs dataset. Or wait one second, if I can just show you this. So this is the link that you can use. So w get, and then you can download your data set from this particular website. Okay, I won't be doing that because I already have it downloaded and I don't want to waste your time. When you're going to download this, you will find different folders over here, and we're going to look at those folders using the code. So we're going to import OS, and we will say that our base directory is called cats and dogs filter, which is this thing, and we're going to print the contents of the base directory, which will be print os.list directories for our base directory. Okay, so you can see that over here we have three files: train, validation, and vectorize. Similarly, if we want to print the contents, so if we want to print the contents of the train directory, then that will be um, adding that will be f base directory and then slash train. And in fact, if you look over here inside, you will also find cats and dogs. Similarly, you can do the same thing for validation as well. So validation, and in fact you will also find cats and dogs over here as well. Now what we're going to do is we want to create directories. Okay, we want to not create directories, we want to save the path for our training directory. So we'll say training directory will be os.path.join base directory comma train. We will be doing the same for our validation directory as well. os.path.join base directory comma validation. And then what I could do is I can show you the but before I show you that, I also need to create one for training. So my training cats directory will be os.path.join train directory comma cats, which is this thing, and training dog directory will be dogs. And similarly, we can do this for testing as well. You can call it validation, you can call it testing, I'll call it validation. So my validation cat directory will be this, but instead we'll have this thing here, we don't need this. Similarly, dog, dogs. All right, so we have all of our directories set up. Now if I want to show you the amount of images that we have, or in fact if the images are going to be read or not, I can write train the cat file names, which will be os.list directories from my train cat directory. And similarly I can also write validation, and let's call this the validation cat directory, and I will be printing not all of the directories but the first 10 directories. And similarly this thing as well. So you can see that it is in fact reading the folders and finding these files over here. Okay, if you want to look at as to how many images do we have, then for that we can say that the number of training cat images are going to be length of train cat f cat f names, and we can copy this and we can say the dogs will be dogs. Have I created one for dogs? I have not created one for dogs, so let's do this very quickly. um, in fact uh, yes, so let's call this dog, and then we can copy this and we can paste this and we can call this dog and dog and dog. Okay, so train dog f names, and then we can copy this and we can write okay, how about the validation, and then this will become validation and this will become the dog. So with this you'll see that I have around 1000 training cat images, 1000 training dog images, 500 cat images, and 500 dog images. Okay, and even if I show you this, so let's show this in the folder, so reveal in file folder cats. So this is for the training, and there are about 1000 images. Now if you look over here, the dimensions of the images is not constant. It's 300 by 280, and if you look over here for this one, this is going to be something different, which will be 237 by 173. So whenever we are training our model, we need to make sure that there is a constant image size. So for that, we'll be defining our image size as, so our image size will be 150 by 150. And also it is not a good practice for you to train your images one by one. So as we were doing over here, we were like sending all of the images when we were training our model uh, over here, right? Another better practice is to send your data in the form of batch size, or in the form of batches. So we have declared our batch size. Next what we're going to do is we are going to create our data generator. Okay, so ideally what we are doing is we are defining a data pipeline. So for my training data generator, I will have training um, my training directory, which will have the cat images and the dog images. Similarly, when I'm going to be creating my validation data generator, I'll be defining a validation directory with its cats and its dogs. So this is what we're doing. So now the next thing that we're going to do is we are going to create this generators. So for that we'll say train data generator, which will be image dataset from directory. And over here we'll say that the first we're going to define our training directory, which will do all of this stuff on its own. And we will set our batch size to be batch size, and we'll set our image size to be image size. So like this, similarly we're also going to create our validation data generator, and over here instead of training directory we'll say validation directory, and the images will look the same. So now if we do this, you can see for the first one it said that it found 2000 files, which is 1000 plus 1000 for both the cat and dogs, for two classes cats and dogs. So the entire purpose of this is, if you can structure your data in this type of format where you have your train separate and your validation separate, and then you have your classes as your folders, it becomes very easy for you to interact with TensorFlow. And you will see in a little while as to why it is. Because unlike before over here, where we wanted to find the class name of this, what we could do over here is we can just say that our class names is going to be train data generator dot class names, and then we can print our class names like this. And now if I want to show you the images from the data generator, what I could do is I could import matplot.pyplot as plot. I can plot a figure of, let's say, fixed size 10 by 10, 10 by 10, and I can say that for images comma labels in my train data generator dot take, which means I'm randomly taking any one batch of 20 images from my training data generator. This can include both the images of cats or the dogs. And over there, what we're going to do is we are going to display 9 images. So for I in range of 9, we will set our axes as plot dot subplot 3 by 3 by I plus 1, and we're going to show our images. But over here, if I go and show you the training generator, it is some sort of like tensor object, okay? And even if I do like say image equals to like train data generator dot take one, and if I show you the image, this is again a TensorFlow object. So if you remember earlier over here when we were doing I'm show, we had to have a numpy.d array. So to do this, it's very simple. What we are going to do is we're going to take our images I, and we're going to convert that into numpy. We'll make sure that it is in the form of integer. So we'll say ut unicode it in int 8, and now uh, I can show my images using the plot. And let's say the title of this plot is going to be class names, and then labels I, and let's set the access to be false. And with this, when we run this, we will find that the title for each of the images is for its respective class. So 9 means we have 1, 2, 3, 4, 5, 6, 7, 8, 9 images. 3 by 3 I plus 1 basically says, okay, this is for this plot 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is this line. We converted each of the images uh, into into what, into numpy and into integer 8, so that we can actually show the images. And then what we did was we said, okay, for the images I, for the labels I, uh, get the class names. So if I remove this, it will show you different images, and it will be showing you labels like this. So label 0 1 0 1 1 1. Since we can read our class names like this, so if I say my class name 0, this will represent cats. If I write class names as 1, this will represent as dogs. So instead of like writing 0 1 over here, what I did was I said class names, and then we encapsulated that inside here. And with that, we got our proper class labels as well. So once you get familiar with using this data generators, it becomes very easy for you to work with your data. Now, the next thing that we have to do is I'll show you the image or the tensor shape. So over here, if I write train images 0 dot shape, this will show you a size of 28 by 28. Okay. However, if I write again for image batch comma labels batch in my train data generator, I just want to take like one batch, which will be, you can also like say dot take one, and over here you'll say image batch dot shape and paste this with the labels batch, and you will find that the shape is now 150 153 now, and also you have 20. So what is this? What does this mean? Well, I will be creating another video, I think so, in the future, where I'll be explaining the normal basics of tensors and how tensors are working in TensorFlow. But ideally, what happens is that you have a rank 0 tensor, a rank 1 tensor, a rank 2 tensor, and a rank 3 tensor, and so on and so forth. Okay, so a rank 0 tensor is basically just a constant value. Okay, it is just a constant value. A rank 1 is you can call it like a vector or a one-dimensional array. Okay, a rank 2 is a matrix which will be of two-dimensional, which will be a 2D array. So this will be a 2D array. So m by n, or whatever you can notations you can use. So you can remember this with a very simple way as to how I remember this, which is if the rank is 2, it denotes 2 by 2. It denotes two values. If it's 1, then it would denote only one value. Okay, so 28 or something like that. So over here, you'll see that 20 comma means that there are 20 values. This one is a rank 1. I think so, if I'm not wrong. Maybe this is the code for the rank, determining the rank. No. Uh, let's see. Uh, Rank for tensors. It's called tf.rank. So tf.rank of this thing over here, and you'll see that in fact it is 1. What is this? This is going to be 1 2 3 4, so the rank of this is going to be 4. Okay, so we're going to do this, and okay, oh, because it was a shape, that's why. So we get 4. Okay, very simple, very easy, not that difficult. So let's go back and let's call this shape. All right, so the next thing is um yes, so I was talking about this now. um think of your ranks as adding more and more information. Okay, so in the first example, when we were using fmnist, we know that we had an image, right? But the image is basically made up of lots of loads of pixels. All right, now a pixel, right? This pixel will be either black or it will be either white. So what we did was we said, okay, I have one pixel and I know that this will be either black or it will be white. If I don't have one pixel but instead I have an entire image, then now I can say that I will have a 28 by 28 image. So 28 by 28 times one pixel. So you can see over here, first we started with pixel, then we added more information which is about the image. What is the image size? Okay. If I write over here as 28 by 28 by 3, this will say that this can take three different channel values, which is going to be red, green, blue. Okay. So again, the more dimensions that you're adding, the more information that you're talking about. Now, another information that I gave over here for this one was this 20. What is this 20? This is the batch size. So I'm saying that, hey, there are there is going to be a colored pixel of this dimension. So there will be an image of this dimension with colored pixels. And how many images are there going to be? There will be 20 images, a batch of 20 images, a batch of 20 images. So remember that the more amount of dimensions that you're adding, the more information you're adding to your tensor. Okay, so this is basically saying that this is 20 labels for your batch 20. All right, so moving on, hopefully this is clear. um, Now what we're going to do next is, now that we've looked at the entire data set, now we even have separated our training data set, the validation data set separately. What we're going to do now is we're going to create our model. So how do we create our model? We are going to write model equals to, um, let me import Keras layers because it becomes much more easier for me to write the entire statement. So here we'll write keras dot models dot sequential, and then we are going to write layers dot. Okay, so before I create my entire network, okay, before I'm going to create that, let me tell you one thing, which is that whenever you're working with your this training data generator, right? We also need to do the first step that we were doing was, before we were sending the data to our model, we were normalizing it, right? Whenever we're working with data generators, we can normalize our data set in two different ways. One way is to use this process method, which is your own custom method, which is like process, and then you send your image, you send your label, and then you can say something like image equals to tf dot cast, image comma tf dot float 32 divided by 255.0, and then returning your image and your label, and then you're using this process for your process method for all of the images over here, and then sending and then putting that into your data generator and validation data generator. So you can do it either doing like this, or another way, or a much more cleaner way to do this is by adding the rescaling module to your sequential model itself. So how do we do that? The way as to how you're going to do that is going to be, I'll show you two different ways. The first way is by saying, hey, my rescale is basically going to be keras.model models.sequence whoops dot sequential, and then you can write layers dot rescaling, and then 1 dot divided by 255. And then what you can do is you can define your entire network, which will be conf 2D. You will have 64. Let's set 3 by 3. Let's set the activation to be relu. Okay. Um, my input image, input shape is basically what? It's basically 150 by 150 by 3. Uh, yes, so there should be one more here. So remember that this inner bracket is for the shape. And then I'll say that my layers dot max pooling will be of 2 by 2, and then I can just copy this, paste this, remove the input shape because we don't need that anymore. And again, let's do this like 16, 32, and then 64. So slowly adding it up, and this as 64, and then we're going to do layers dot flatten, and then we're going to do layers dot dense. Let's add 512 neurons again with the activation function of relu, and let's say that we'll add layers dot dense again, and we have 1 comma activation, and let's call this as sigmoid. All right, so what you could do is before you run this entire model, you can just add rescale over here. Simple as that. And that will create your model. If I do model.summary, you'll get your entire model. The one thing, the one disadvantage is that you won't actually get your output shapes. I don't know, this is some new feature of TensorFlow where it's not compiling this. So one trick that you could do is you can just remove this, look at the shape, and then you can add it, because your rescale basically won't um, it won't add any parameters. So one thing that you could do is you could say, hey, model or rescale dot summary. You could do this, and then you can say other model. You can remove this, and then you can do other model dot summary. So other model dot summary, you'll get this entire thing, and then you can just say that model equals to keras dot models dot sequential, and then add your rescale to this, and then your other model, and then you can run this, and you'll see that your parameters 9 for all of this and this. So again, you can play around with this, but for simplicity, I'll just keep this to one model, and I will also add the rescaling part over here. So I'll remove this, I'll remove this, I'll remove this as well, and this one as well. I'll run this, and I have my entire model with question marks. Now the next thing that we're going to do is we're going to compile our model. Before I get into the compilation, why did we use sigmoid over here? Because it's a binary classification problem. Either the class is going to be cats or either it's going to be dogs. That's the reason why I have chosen the sigmoid activation function. Now what we're going to do is we're going to define our hyperparameters, which are going to be for this case scenario, I'll be using tensorflow.keras.optimizers, and we're going to be importing rs, root means to square prop, and then model.compile, we'll say that our optimizer is rms prop, and let's set the learning rate to be about 0.001, our loss to be binary cross entropy because it's a binary classification problem, and we are going to set our metrics metric. Okay, so okay, where is the whoa 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 whoa, there we go. And then let's set our metrics to be uh, accuracy k rms, there we go, root mean squared. And then set that our history is going to be model.fit, so I'm basically adding the model in this history um, object. And then we can say train data generator, and then validation underscore data is going to be validation data generator, and then let's set our epochs to be about 10. So while this is being executed, let's try to find a way as to how we can save our model. So save model in TensorFlow. So we need to install this, and then we can create our model. This will return a model. We got the model. We did model.summary. Okay, and then we said checkpointing, which is going to be this. So let's say that we add, I can't add a cell, I'll just add this over here. Um, Callbacks, model.checkpoint file path this, save waits to true, verbose to this. Yes, let's do that. And then I need to call this thing over here. Hmm. Yeah, so we can manually save them as well. So one way to how to do this is you can save checkpoints during training, which is by using callbacks. Okay. So callbacks is very powerful. Um, and the other way, the easier way to do this is you can just create or save your model once the training has been completed. So there we go. Once it has been saved, you can just write this thing here. So you can just do this. Let's create a checkpoints, sorry, a folder called checkpoints, and we created it, and then you can load this. So this will be used for loading it, and we can get the evaluation as well. This will be used afterwards. So this is basically just saving the weights, and if you want to save the entire model, you can use this thing which will save this as Keras model over here. So again, there are different ways as to how you can do this. Right now I'm just going to save my weights, and it did not because I need to specify dot weights dot h5, and if we go here, in fact our checkpoints have been saved. If we go back and we load our model over here, what we could do is now we can just load the weights We can just load the weights. Again, we need to call this as weights.h5. Uh, okay, maybe this thing. Okay, so there's some error. Anyways, I will make another video on how to like save your checkpoints and all of these models in the next video. I've forgotten the syntax right now, so I won't be going into that. Anyways, so our model has been trained, and the next thing that we are going to do is we are now going to evaluate this. So for evaluation, we are going to say that our accuracy is going to be history.history and set this to accuracy. Our validation accuracy is going to be, again, let's just call this entire thing here, paste this, let's call this val accuracy. Let's set the loss to be history.history.loss, and then copy paste, and then this will be your val loss, and this will be your val loss over here. And then we can say that our epochs are going to be the range of length of accuracy, and then we're going to plot our we're going to do plot the epochs and our accuracy. We're going to plot epochs val accuracy, and we'll say that the title is going to be training and validate and validation accuracy, and we are going to show this. So we got an error which is val loss does not exist because L was capital and we saw our first plot. We can copy this and we can create another one. In this case, we're going to be showing it for loss and val loss, and we'll call this as loss. So you can see that the training your training accuracy, which was 0.531, which was this one, and then it started increasing over here. And um, 1 second. Yes. So your training accuracy was increasing, but your validation accuracy was not increasing at all. And if you look at the loss, the training loss was decreasing, but the validation loss is increasing. And you can also see over here is that the validation loss is increasing. So why is this happening? The reason is because you don't have enough images of cats and dogs. Um, so maybe um, your cat, maybe your data set might not have an image of a cat where it has been flipped. So I'm not sure if I can do this here. Where it has been flipped vertical, where it has been where it has been flipped horizontal, and the image just disappeared. Wait, there we go. So the image has been flipped horizontal, or it has rotated a little bit, or maybe that the cat is a little bit skewed like this. Maybe that there is a cat which was laying down like this. My terrible drawing skills are at its perfection now. Maybe a cat was laying like this. So what you could do is you can kind of like without with using the same data set that you have, you can like stretch this. So let's rotate this by about 90. And let's flip this horizontal. We can like stretch this out, maybe something similar to that. So all of this is known as data augmentation. So one way to reduce overfitting is by adding more data and showing more data to our model. So what we're going to do is we're going to copy this and we're going to paste this, and now we will call this as data augmentation. So now we will look at data augmentation. So how to do data augmentation? Let's do this. And for data augmentation, the steps are more or less the exact same that we've been doing. That's the reason why as to why I copied this. So we're going to do all of this, all of this, all of this, all of this, all of that, that, and we're going to stop till here, which is over here. We're not using this. Now what we're going to do is instead of adding rescaling, we can also add different augmentations, which would be, we can say augmentation will be keras.models.sequential. First, what I want you to do is I want you to do rescaling. So I remove that and I'll put this here. Next, what I want you to do is do random rotation of 0.1. So if you don't know what this basically is doing, you can always go over here, write random rotation, go to its documentation and view as to what it's doing. So random rotation will basically rotate the image during the training process. You have different parameters which you can play with. You can have values from 0 to 255. Over here, if I remember correctly, this is some other value range. If I remember correctly, 0.1 refers to uh, zero point 0.1 radians. And if you convert radians of zero point 0.1, this will become a rotation of like 40 degrees. So you can do that, and then you can say that your layers dot random translation could be of width factor 0 0.2 and the height factor as 0 0.2, which means that maybe if I have an image, instead of like keeping my image to the centered, I can maybe move this a little bit to the right. So maybe a little bit to the right. The next thing that we're going to do is we can also zoom in and zoom out our images. So layers dot random zoom of let's say zero point 0.2, and again let's set the random flip to be horizontal. Once we've defined this, we can add this over here and we're pretty much done. That's it. And then we can train our model again, and we will be doing a little bit of inference in this one. So while this is being executed, I'll write the code for inference. So for inference, I have a test image over here of a cat. It's this one, and let's see what it predicts. Does it predict it as a cat or a dog? So for this, I'll say from tensorflow dot keras dot utils, I'm going to import load image and image to array. I will import numpy as np. I will import os. I'll say that my path is going to be my test images slash images.jpg, and then image is going to be load the image of this path with a target size of 150 by 150. Why 150 by 150? Because this is what my model is going to expect. So we are going to do this. And also over here, you need to know that whichever transformations that you're applying over here, you also need to apply this for inference as well. As of yet, these will not actually change the size or the pixel values, but this will definitely change the values from 0 to 255 to between 0 to 1. So it's very important for you to also add the same step of inference, the step of normalizing this over here as well. So first of all, we're going to convert the image into an array. Once we've done that, we're going to divide equals to by 255, normalizing it, and then we can say print before expand dims. This will be x dot shape, and then we will do x equals to np dot expand dims x comma axis as 0, and you will see what this expand dims is and why are we doing this in a little while. And then we'll say after expand dims, and then we'll say x dot shape, and then we'll say that our class is equals to model dot predict x comma, let's set the batch size to be about batch size, and then let's print the classes, and then we can say that if the classes 0 is greater than 0.5, which is for the uh, we'll say that this is a dog, else we will say that this is a cat. Okay, so our training is done. Let's take a look at the graphs, and you'll see that the validation loss is now decreasing. Okay, it's doing a little bit increasing, but if you compare this graph, no, I not save? I did not save. I did not save. But anyways, if you go back and you look at the graphs, you will see that this is improving now. So anyways, this was the code for inference. So let me put this code down there. And yes, so let's run this. So before expandins, you had an image of 150, 153, which is expected. But remember that when we were training our model over here, the training data that we gave had a batch size. So you had another like dimension over here. So to do that, we've done the same thing. We have expanded one more dimension over here, because if you don't do that, the model will say, hey, I do not understand this, what is this? Okay, and then for model predict, you just say batch size is 20. You can, instead of like sending one images, you can like send 20 images and it can do prediction for 20 images. But in this case, we're just doing it for one. And then you can say that classes will basically predict you the probabilities. Okay, and we said that if the probability is greater than 0.5, we'll say that it's a dog, otherwise we'll say it's a cat. And it did predict it successfully, which was it was a cat. Now if you remember from the previous session or previous example, which was class names, the 0 represents the cats, which is that if it is lesser than 0.5, then it will be a cat. So what we could do is we can say that if it is greater than uh, I'll have to approximate it to about 0. Yeah, it's going to be really really complicated, so I won't go into that. Anyways, so this is how the prediction is being done and the data augmentation is completed. Now there is one last thing that I need to tell you guys, and maybe that is going to mark the end of this video, which is how to use models which are already trained on some data set, and you are going to use those models. So basically what I'm trying to say is how to apply transfer learning. So to apply transfer learning, I'll copy this and I'll make another file. So we'll call this transfer learning. Over here, we need a little bit more libraries. So one library that we're going to import, so from tensorflow.keras.applications, we are going to import Inception v3 model, and we are also going to uh, say that from uh, TensorFlow or from Keras, we are going to import layers and model, and from Keras dot uh, yeah, I think so. We don't need that. Okay, so we do the step, we do the step, we do this, all of the steps, and then we get to the image size, and then we create this thing. Now what we're gonna do is I'll remove all of the unnecessary code. Uh, we don't even need this. We don't even need this thing. We have our data augmentation set up, and now comes the part where we need to add our model. So all right, so yeah, let me resume. So what we're going to do is we are first going to load the model or the weights. So local weight file is going to be inside my models. I've already downloaded this. I will wait. All right. So the weights for the model of Inception v3 are, you can get them from over here. Okay. So I've already downloaded that, and I'll be just importing this. So Inception v3 weights. Okay. So we're going to do this. Now the pre-trained model, trained model. The pre-trained model is going to be called v Inception v3, where the input shape is going to be 150 by 150 by 3, like we were mentioning over here. The We're not going to include the top. So essentially what we are doing over here is we are also applying uh, I forgot the name. There was um, it's one is called transfer learning, and the other one is called yeah. So what we are doing over here is we have a neural network. Okay, so we have a neural network, and over here, um, the last layer, this last layer, we're removing that. We're saying that we don't need this. Okay, and the reason as to why we're doing this is because you can imagine that this neural network was trained on some other problem which had two neurons. Okay, but in our case we don't want this neural network. We want one where we have one neuron at the end. Okay, so what we're going to do is we're going to remove this. So to remove this, we are adding this include underscore top as false, and the next thing that we're going to do is we are going to set our weights to be false. So this will come afterwards. We'll set this to weights as none, and then what I can do is I can show you this model. So I'll do pre-trained model, this thing, and I need to run it from the top. So let me comment this up, and then Let's run everything above. Okay, very, very quickly. Now let's run this. And now, okay, yes. So when I'm going to do summary over here, okay, I have removed the top. So you'll see this is a very, 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 very big neural network where at the end I have 3 by 3, and then I have this concatenate and there's 93 over here. So the trainable parameters are 21,000 something something. Now if I do this as true, and now if I show you the training, the model, now you can see that the size has increased by 23,000 and the last prediction is for 1,000 neurons. Okay, so again we don't need these many neurons at the last layer. That's the reason why we have removed the top part. So we are going to set this to false. Okay, so we've done this, and then we are going to include this file over here, or you can also do include this over here. And then what we're going to do is we're going to now add weights to this model. So how are we going to add weights? Again. It's going to be set by pre-trained model dot weights or load load weights, and that will be by saying as local weights file. Okay, so now it has loaded. It's not going to be equals to, it's a function. So now it has loaded the weights. Next thing we're going to do is we're going to say that for layer in the pre-trained model dot layers, we're going to set layer dot trainable equals to false. So what this is basically doing is this is saying that, hey, this network that we had over here, we set our weights from the some file that I had downloaded earlier, and what I want you to do is I want you to lock this up. Okay, I want you to lock this up. So what I'm going to do next is I'm going to take this part and I'll add my own small neural network to this. So let's say this is my neural network, and what you are going to do is you are allowed to train all of these connections or these parameters, or you can train this model, but you are not allowed to mess anything with this model whatsoever. So that is what we have done with this, and we are setting all of the layers in our inception model as trainable as false so that we do not mess with them. And lastly, what we're going to do is we're going to say that layer or last layer, we want to get the last layer from the pre-trained model dot get layer, and you'll see that there are a lot of layers. Okay, there are like lots of layers, but the one that we want is going to be, you can see that there's also called mix 8, there will be a mix 9, and so on and so forth. But we don't want this network at all, not this, none of this. We want to get the network till here. So from the start till till mix 7. Okay, you can choose to also include 8, 9, 10 as well, but in our case we will just get the model till the layer of mix 7. So I'll call this as mix 7, and we will see what is the shape. So we'll say that the last output equals to last layer dot output, and then let's just say last, or let's just run this. and let's just say that last output. So you'll see that this is a 7 by 7 by 768, and if you want to get the shape, it will again say the same thing, which is 776 768. Now, instead of using a sequential API to build our model, since we are connecting this with another model, the other way as to how you're going to do this is you will define your layers in this format, which is layers.flatten from the last output. Then you will say that x equals to layers.dense, and then you will set that you will have 124 neurons with the activation as ReLU, and you are going to connect this layer with this one by mentioning x like this. Okay, if you don't mention it x like this, you are basically doing this thing, which is you're getting a network like this, or you got a network like this, and you got a network like this, and there are no connections between them. So to connect them, you need to add the last layer, which is this x over here. Okay, and to even to even decrease the amount of overfitting, because we are using a very big model. Okay, whenever you're using a very big model, there is a chance of overfitting, because there are going to be a lot of cases where your model is going to be, it's going to start learning your data set. Okay, whenever you have very big models, it's always good practice to use dropouts. So what is dropouts will basically randomly, for some value, if I say 0.2, then for each of the layers there is a 20% chance that it will, I think it's so, it will, for each layer, I think, if I remember correctly, before I make any guesses, I'll just search this over here. So layers dot dropout. Before I tell you something wrong, it's better to tell you. Yes, 20%. Yes. So if you define this as zero point 0.2, then 20% of the neurons in the first layer will be dropped. So this is what dropout does. Okay. Um, okay. So we are setting our dropout rate to be about 0 0.2 to avoid overfitting, so that we can decrease the complexity of our model. So we'll set this as layers dot dropout to zero point 0.2, add an x over here, and then we'll say that our last is going to be a dense layer of 1 comma activation as sigmoid, and we will add x over here. And lastly, we'll say that our model is going to be model, and we're going to say pre-trained model dot input. Okay, so grab the input from here and then connect that with x. We can do this, and then we can write model of summary, and this will show you the entire summary, which is that we added the input layer of 150 153, which was this thing. Then we have, um, the entire inception v3 model. At the very end, um, over here we flattened our mix 7 layer, and then we added a dense layer of 1024, we added dropout, and then we have a dense layer of 1. So that's what we've done. And after this, so let me just remove its output. We're not going to be using this anymore, not this anymore. For the optimizers, before I add the optimizers, I also need to add my augmentation layer as well. So what I can say is my augmented model is going to be keras.sequential, and then I can say data augmentation, and then I can add my model over here, and then I can compile this as I do, but I'll call this as augmented model, and we'll be using RNS prop, and yeah, so let's run this and let us fit the model and see how it performs. Okay, so this is not compiled. There we go. Okay, so you can also do it like this, or um, you can. I'm not sure if you can add augmentation over there. Maybe you could have add. No, I don't think so. You can add augmentation over here. Um, maybe you could do like we could have done model dot keras dot model dot sequential, where we add the data augmentation, then we add the input shape, and I'll have to like add the input shape, right? So yeah, I'll see if I can find better ways to add the augmentation to your model. But up till now, this is like the way as to how I figured out as to how we can do it. So this will take some time, and I haven't turned on the GPU, so that's the reason why it's taking so much time. One thing that you could do is you can add your callbacks in the case if it gets um, if the training becomes very big. So let's add this as well. So callbacks equals to callbacks. Let's run this, and let's say that when it becomes 0.98, that's where you want to stop, and it will do the entire epoch stuff. And I'll speed this up, so I'll pause the recording over here, and once it's complete I'll show you the resultant graphs that we're getting. All right, so the model has been trained. It did not feel the need to it did not feel the need to call the callback. Now if we take a look at the graphs, if I can show you the graph. Okay, so that's the previous one, and plot is not mentioned, so we are going to do import matplotlib dot pyplot as plot. Now if I do this, you'll see that now it's a bit better because the validation accuracy is also increasing. There's less fluctuations, and it's starting with 0.95 and somewhere over there. Similarly, the training accuracy is also increasing, and there is less fluctuations in your overall training loss. So the loss over here is about 0.6, whereas with the transfer learning it is only 0.01, which is very good. Now lastly, we can also do our inference, and you can see that it is more confident now. The values are very less, and it is now predicting it as a cat. So that was all with this video. I hope now you have a better intuition as to how to work with convolution neural networks, how to add data augmentations, how to do transfer learning. For hyperparameter tuning, I'll see if I can make another video on that, but you can change different values over here. You can set some variables, and with that you can do your stuff. So in the next video I'll be taking a look at the NLP, section of TensorFlow, and after that, if I get the time, then I'll make a video on weights, saving weights, and using TensorBoard logs. So in hopefully in the next video or in the next video, I'll be showing you all of that. So thank you and see you in the next one.